Set theory is the study of sets, understood informally as collections or groupings of objects. The objects collected in a set are called its elements or members. Typical examples include the set of natural numbers, the set of prime numbers, the set of books on a shelf, or the set of points on a line. Set theory aims to clarify what sets are, how they relate to one another, and how they can be used to construct and analyze mathematical objects. So-called naive set theory is an informal and intuitive approach to sets. It relies on ordinary reasoning about collections and does not impose strict formal restrictions on what counts as a legitimate set. This contrasts with axiomatic set theories, such as Zermelo-Fraenkel's set theory, which were developed to avoid paradoxes that arise in the naive approach. One important motivation for set theory is its unifying power. Very different kinds of mathematical objects, numbers, functions, relations, geometrical figures, can all be described in terms of sets. This suggests that set theory provides a common foundational language for mathematics. Another motivation is clarity and precision. Informal mathematical reasoning often appeals to collections, domains, or ranges without explicitly defining them. Set theory provides explicit tools for talking about such collections and their properties. Finally, set theory plays a crucial role in foundational investigations. Questions about the nature of infinity, mathematical existence, and mathematical structure are naturally expressed in set theoretic terms. Set theory is often regarded as a foundation for mathematics. Many mathematical theories can be reduced to or reconstructed within set theory. For example, each number can be defined as a specific type of set, relations as sets of ordered sets, and functions as special kinds of sets of ordered pairs. This reduction does not mean that mathematicians consciously think in set theoretic terms when doing everyday mathematics. Rather, it shows that, in principle, mathematics can be given a unified underlying framework. From this perspective, set theory serves as a background theory that supports and legitimizes mathematical practice. However, some philosophers argue that not all of mathematics is best understood as really about sets. Even so, set theory remains very important as a common technical language. Set theory is closely related to logic, but the two are not identical. Logic studies valid reasoning and inference, whereas set theory studies collections of objects. Still, logicians routinely use set theoretic concepts, especially in metalogic, where one reasons about logical systems themselves. For example, when defining a formal language, logicians describe sets of symbols, sets of formulas, and sets of proofs. Semantic notions such as models, interpretations, and truth assignments are typically defined using sets and functions. Even if set theory is not itself logic, it is deeply embedded in logical methodology. Informally, a set is a collection of distinct objects considered as a whole. The objects may be concrete or abstract. Sets themselves can be elements of other sets. Some authors distinguish between sets and classes. Roughly speaking, classes are collections that may be too large to be sets, such as the collection of all sets. In naive contexts, however, the terms set and class are often used interchangeably and no sharp distinction is drawn. If an object A is an element of a set S, this is written informally as A is in S, and formally as A followed by the symbol for is an element of, followed by S. If A is not an element of S, we write A followed by the symbol for is not an element of, followed by S. Elements of sets may include individual objects, numbers, other sets, ordered pairs, relations, or functions. Two sets are identical if and only if they have exactly the same elements. This principle is often called the principle of extensionality. Two important consequences follow. Order does not matter. The sets whose only members are 1, 2, and 3, and 3, 2, and 1, respectively, are the same set. Repetition does not matter. The set whose only members are 1, 1, and 2 is the same as the set whose only members are 1 and 2. Thus, sets are determined solely by their members. There are two standard ways to describe a set: by listing its elements. Example, the set whose only elements are 1, 2, and 3. By a condition on its elements. Example, the set of all natural numbers less than 4. The second method is often called set builder notation. The set whose only elements are 1, 2, and 3 is identical to the set of all natural numbers less than 4, given that we do not count 0 as a natural number and is less than is interpreted as usual. Note that the number 1 is not identical to the set whose only element is the number 1. The universe, or universe of discourse, sometimes referred to by the letter U, is the total collection of objects under consideration in a given context. What counts as the universe depends on the discussion. In arithmetic, the universe might be the natural numbers. In geometry, points or regions. In set theory, often sets themselves. The empty set, the set that does not have any elements, is often written the left curly bracket immediately followed by the right curly bracket, or a slashed circle. A set A is a subset of a set B if and only if every element of A is also an element of B. A is a proper subset of B if and only if. A is a subset of B, but A is not identical to B. Example, the set whose only members are 1 and 2 is both a subset and a proper subset of the set whose only elements are 1, 2, and 3. The set whose only members are 1, 2, and 3 is a subset of itself, but this set is not a proper subset of itself. The set A is identical to the set B if and only if A is a subset of B and B is a subset of A. The union of A and B is the set of all elements that are in A or in B. The intersection of A and B is the set of all elements that are in both A and B. The difference of two sets A and B is the set of elements in A but not in B. Complement. Relative to a universe U, the complement of A is the difference of U and A, that is, the set of elements in the universe but not in A. Given a collection of sets, the big union is the union of all of them, and the big intersection is the intersection of all of them. Examples: the union of the set whose only members are 1 and 2, and the set whose only member is 3 is the set whose only elements are 1, 2, and 3. The intersection of the set whose only members are 1, 2, and 3, and the set whose only members are 2, 3, and 4 is the set whose only elements are 2 and 3. The difference of the set whose only elements are 1, 2, and 3 and the set whose only members are 2 and 3 is the set whose only element is 1. If the universe includes 1, 2, 3, and 4 and nothing else, and A is the set whose only members are 1 and 2, then the complement of A is the set whose only elements are 3 and 4. Two sets are called disjoint if and only if their intersection is empty. The set whose only members are 1 and 2 and the set whose only members are 3 and 4 are disjoint. The power set of a set A, often written P, left parenthesis, A, right parenthesis, is the set of all subsets of A. If A has n elements, then the power set of A has 2 to the power of n elements. Example, the power set of the set whose only members are 1 and 2 includes the empty set, the set whose only member is 1, the set whose only member is 2, and the set whose only members are 1 and 2. We can speak of ordered sets, ordered pairs, ordered triples, ordered quadruples, etc., often written A, B, C, A, B, C, D, etc. The first component or element or member of the ordered pair A, B is A, and the second component or element or member is B, and so on. An ordered set is a set where order matters. The ordered pair A, B is identical to the ordered pair C, D if and only if A is identical to C and B is identical to D. The ordered triple A, B, C is identical to D, E, F, if and only if A is identical to D, B is identical to E, and C is identical to F. And so on. Two important consequences follow. Order does matter. The ordered set 1, 2, 3 is not identical to the ordered set 3, 2, 1. Repetition does matter. The ordered set 1, 2, 1 is not the same as the ordered set 1, 2. 1, 2, 1 is an ordered triple, and 1, 2 is an ordered pair. Thus, ordered sets are not determined solely by their members, but also by the order of their elements. We can speak of binary relations, trinary relations, quaternary relations, and so on. X is longer than Y expresses a binary relation, X stands between Y and Z expresses a trinary relation, and X promises Y to do Z before T expresses a quaternary relation, etc. In set theory, relations are often identified with sets of ordered sets. A binary relation is a set of ordered pairs, a trinary relation is a set of ordered triples, a quaternary relation is a set of ordered quadruples, etc. We will focus on binary relations in this introduction, such as is larger than, is a parent of, or is equal to. A binary relation on a set A, or between elements of one set A and those of another set B, is then any set of ordered pairs whose two components are both elements of A, or whose first component is an element of A and whose second component is an element of B. One often writes A, R, B, or R, A, B for A, B is an element of R. The domain of a binary relation is the set of first elements of its pairs, and the field, or range, or codomain, is the set of second elements. In set theory, A cross B, or A times B, denotes the Cartesian product of two sets, A and B. Let A and B be sets. The Cartesian product A cross B is defined as A cross B is identical to the set of all ordered pairs A, B such that A is an element in the set A and B is an element in the set B. That is, A times B is the set of all ordered pairs whose first component comes from A and whose second component comes from B. Note that A times B is not identical to B times A. One can think of A cross B as a grid of points, all possible combinations of elements from A and B, or the space of possible pairings between elements of two sets. This is often used when defining relations on a set. Example, let A be the set 1, 2, 3. Then A cross A is identical to the set, whose only members are the following ordered sets 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, and 3, 3. A binary relation from A to B is any subset of the Cartesian product of A and B. A relation on A is a subset of the Cartesian product of A and A. A function from A to B is a special kind of subset of the Cartesian product of A and B, satisfying additional conditions. We will say more about this later. The concept of the Cartesian product can be generalized to 3 sets, 4 sets, and so on. We can speak of multiple Cartesian products. For example, A cross B cross C is identical to the set of all ordered triples A, B, C, such that A is in A, B is in B, and C is in C, etc. There are different types of relations, for example, reflexive, symmetric, and transitive. A relation R is reflexive if, and only if, every element stands in R to itself. Examples: equality, less than or equal to. A relation R is symmetric if, and only if, for all x and y, if x stands in R to y, then y stands in R to x. Examples: equality is a sibling of. A relation R is transitive if and only if for all x, y and z, if x stands in R to y and y stands in R to z, then x stands in R to z. Examples: greater than is a subset of. These concepts are often restricted to certain sets. So we can, for example, say that a relation R is reflexive in the set A if and only if for all x in A, x stands in R to itself, and so on. Hence, a relation can be reflexive in a certain set without being totally or absolutely reflexive, reflexive in the whole universe, symmetric without being totally or absolutely symmetric, etc. In this introduction, we will often ignore this point. Given a set A, the identity relation on A, often written IA, where A is in subscript, is defined as A is identical to the set of all ordered pairs A, such that A is an element in A. In words, every element is related via the identity relation to itself and only to itself. Example: let A be the set whose only elements are 1, 2, and 3. Then the identity relation on A is the set whose only members are the ordered pairs 1, 1, 2, 2, and 3, 3. The identity relation is reflexive, symmetric, and transitive. A relation is an equivalence relation if and only if it is reflexive, symmetric, and transitive. Equality is an example of an equivalence relation, but there are also many other equivalence relations. For example, has the same age as in the class of all people. Let E be an equivalence relation. Then the set of all B such that A stands in E to B is called the equivalence class of A. A partition of a set A is a set X of subsets of A, such that any two distinct sets in X are disjoint, and the union of all the sets in X is all of A. The notions of equivalence and partition are related by the fact that if E is an equivalence relation on the set A, then the set of E equivalence classes is a partition of A, while if X is a partition of A, then the relation A, E, B, defined to hold if and only if A and B belong to the same set in X, is an equivalence relation on A. A fundamental fact about equivalence classes is that every object in the domain is in exactly one equivalence class. There are several kinds of order relations. Order relations are typically reflexive or irreflexive, antisymmetric, and transitive. Some are connected. A relation R is antisymmetric if and only if for all x and y, if x are y and y are x, then x equals y. A relation is connected if and only if for all x and y such that x is not identical to y, either x are y or y are x. Examples of order relations include less than, greater than, less than or equal to, is a proper subset of, and is a subset of. A well-order R on a set A is an order with the property that every non-empty subset of A has an R least element. The usual order on the natural numbers is a well-order in this sense. Let R be a binary relation from a set A to a set B, that is, R is a subset of the Cartesian product of A and B. The converse or inverse of R, often written R minus 1, where minus 1 is in superscript, is defined as the converse of R is identical to the set of all ordered pairs B, A such that A, B is in R. In words, the converse relation is obtained by reversing the order of each ordered pair in the original relation. Examples: let R be the set whose only elements are the ordered pairs 1, 2, and 3, 4. Then the converse relation is the set whose only elements are the ordered pairs 2, 1, and 4, 3. The converse of the relation is a parent of is the relation is a child of. Let R be a relation from A to B, and S a relation from B to C, R is a subset of the Cartesian product of A and B, and S is a subset of the Cartesian product of B and C. The composition of R and S, often written S ring operator, circle operator, or composition operator R, is defined as S composition operator R is identical to the set of all ordered pairs A, C, such that there is a B in B, such that A, B is in R and B, C is in S. In words, A is related to C by the composition if and only if there is an intermediate element B that connects them via R and S. Examples: let R be this set, whose only members are the ordered pairs 1, 2, and 2, 3, and S be the set, whose only members are the ordered pairs 2, 4, and 3, 5. Then from 1 via R we reach 2, and from 2 via S we reach 4. From 2 via R we reach 3, and from 3 via S we reach 5. So the composition of R and S ring operator R, is the set whose only elements are the ordered pairs 1, 4, and 2, 5. Let R be the relation is a parent of, and S be the relation is a parent of. Then S composition operator R is the relation is a grandparent of. Let R is a subset of A cross B be a relation, and let A prime be a subset of A, and B prime be a subset of B. The restriction of R to A prime cross B prime, often written R the vertical bar A prime cross B prime, is identical to the intersection of R and A prime cross B prime. In words, keep only those pairs in R whose elements lie in the chosen subsets. Example: let R be the set whose only elements are the ordered sets 1, 2, 2, 3, and 3, 4, and A prime be the set whose only members are 1 and 2, and let B prime be the set whose only members are 2 and 3. Then R restricted to A prime times B. Prime is the set whose only elements are the ordered pairs 1, 2, and 2, 3. Closure operations add pairs to a relation so that it satisfies a desired property. The reflexive closure of a relation R, often written R-ref, where ref is in superscript, on a set A is the union of R and the identity relation on A. It is the smallest reflexive relation containing R. Example: let R be the set whose only elements are the ordered pairs 1, 2, and 2, 3, and let A be the set whose only elements are 1, 2, and 3. Then the reflexive closure of R is the set whose only elements are the ordered pairs 1, 1, 2, 2, 3, 3, 1, 2, and 2, 3. Here we have added the ordered sets 1, 1, 2, 2, and 3, 3. The transitive closure of R, usually written R plus, where the plus sign is in superscript, is the smallest transitive relation containing R. Intuitively, it adds all pairs A, C, such that there is a chain of one or more R steps from A to C. Example: let R be the set whose only elements are the ordered sets 1, 2, and 2, 3. Then the transitive closure of R is the set whose only elements are the ordered pairs 1, 2, 2, 3, and 1, 3. Here, 1, 3 is added because 1 R, 2, and 2 R, 3. The reflexive transitive closure of R, often written R star, where the star is in superscript, on a set A, is the union of the transitive closure of R and the identity relation on A. It allows 0 or more steps along the relation. Example: continuing the previous example where R and A are the same sets as above. Then the reflexive transitive closure of R is the set whose only elements are the ordered sets 1, 1, 2, 2, 3, 3, 1, 2, 2, 3, and 1, 3. A function is a special kind of relation in which each element of the domain is related to exactly one element of the range or codomain. In other words, a function from a set A to a set B is a relation, often referred to by f, between elements of A and elements of B, such that for every A in A there is a unique B in B such that A, F, B. The unique B is often written f of A. F of A is identical to B, says the same as A, F, B in this context. A in this construction is often called an argument, and B a value. B is the value f takes for the argument A. A is sometimes called an input and B an output. Functions can be one-to-one, injective, many-to-one, or onto surjective. If for every B in B there is at most one A in A, such that f of A is identical to B, then the function is said to be one-to-one or an injection. A function f is many-to-one if there is an x and a y in the domain, such that f of x is identical to f of y, but x is not identical to y. If for every B in B there is at least one A in A, such that f of A is B, then the function is said to be onto or a surjection. A function that is both an injection and a surjection is called a bijection. A bijection from a set to itself is called a permutation. A binary operation on A is a function from the set of ordered pairs of elements of A to A itself. Addition and multiplication on the usual number systems are examples of operations in this sense. Functions can be composed and some have inverses. The cardinality of a set is a measure of the number of elements in that set. It tells you how big the set is. Let A be the set, whose only elements are 2, 4, and 6. Then the cardinality of A is 3, because there are 3 distinct elements in it. The cardinality of a set S is usually represented in one of 3 ways. We can write the vertical bar followed by S, followed by the vertical bar. We can write N followed by the left parenthesis, followed by S, followed by the right parenthesis, which is an abbreviation of the number of elements in S. And we can write the expression card followed by the left parenthesis, followed by S, followed by the right parenthesis, which is an abbreviation of the cardinality of S. If there is a one-to-one correspondence between 2 sets A and B, that is, if we compare every element in set A with exactly one element in set B without any left over, they have the same cardinality. If there are leftovers in set B after pairing, then the cardinality of B is greater than the cardinality of A. Naive set theory provides an intuitive and powerful framework for understanding collections, relations, and mathematical structure. Although it leads to paradoxes when taken without restriction, it remains an essential starting point for learning set theory and for appreciating its foundational role in much of contemporary logic and mathematics.